How's it going? Let's begin our last week of this unit. We're going to start off with friction. All right, friction, as you may know, is the force that happens when two things make contact with each other. And that is going to be pretty straightforward later on, but basically, everything has friction as long as they're with contact. That is how air resistance happens, is the friction of air with whatever is being launched. Now we have two kinds of friction. We have the static friction and the kinetic friction. Kinetic friction is when things are moving, and static friction is when they're not moving. Now, static friction is the greater of the two. Now think about this. If you're pushing, like say you're pushing a vehicle out of like a ditch or something like that. You gotta push, you push, you push, you push, you push, you push. It's not moving, it's not moving. Then all of a sudden, bam, it starts moving, and then it's a whole lot easier to move. That is because static friction is actually greater than kinetic friction. Okay, the friction while it's moving is greater. It's got some inertia behind it, some force of its own. And no one's entirely sure exactly why friction acts this way. Some people figure it's because of minute imperfections on the surfaces. Uh, some people figure that it's because of electrostatic attraction between the atoms of the surfaces. All that we know for sure is that friction always acts in the direction opposite the motion of the object. So if I have an object that is going this way, my friction will be that way. I just realized it looks like an A. So, and it's always proportional to the normal force. And that's how we're going to calculate it. So, some surfaces, now, what we have to realize is some surfaces have less friction than others. And even if you got two things on the same surface and they're different, that will make a difference. So, for example, there's a big difference you walking on ice as opposed to you walking on the floor of your kitchen. Also, there's a big difference between walking on the floor of your kitchen with your wool socks on and barefoot. Again, the friction is noticeably different. So we have to keep that, we have to take that into account. And we do it using this formula. So our force of kinetic friction is equal to the normal force over here times this constant. It's a constant, we call it mu. Constant. And that is a Greek letter, basically the Greek letter M. Okay, so we can measure this coefficient of friction, and the smaller the number, the less friction. So for example, ice would have, relatively speaking, a lower coefficient of friction. And then, so what we've done is that the physicists have actually come up with a table of different coefficients of friction. Now, this is the table. You are not expected to memorize this. But for example, if you had steel rubbing on steel, here is your kinetic friction, and this one here is your static friction. So don't get them mixed up. Sometimes it is a little tough. Okay, so it actually tells you like steel on steel, glass on glass, rubber on concrete, Teflon on Teflon, synovial joints in humans. Okay, so let's take a look at an example here. We get a 12-kilogram piece of wood is placed on top of another piece of wood. Excuse me. There is 35 newtons of maximum static friction measured between them. Determine the coefficient of static friction between the two pieces of wood. Okay, so this is kind of the way it goes here. So we've got one block of wood and another block of wood. This one here is 12 kilograms. So this means that the force of gravity is going to be 9.81 times 12, right? Which is going to be 117.72 newtons. Now, it turns out that is force of gravity in this case will be the same because I got a force of gravity going down, but then I got a normal force going up. So that's going to be the same as my normal force. Oops, normal. Okay, now that's all well and good. So let's calculate our friction here. Now, because it's not moving, it has to be static friction. Force of friction that is static. And I'm going to say that's equal to mu times my normal force. So I happen to know that there's 35 newtons of static friction. oh, 30. Sorry, let me erase that. Actually, I'll just write 35 newtons. And I'm trying to find this one. And I know that my force was 117.72, which means that my mu is going to be 0.297. Okay, so let's take a look. Now, by all means, please make sure to pause, and if you need to look back on things, feel free. So, for example, I have a steel box sitting on a steel workbench, and I try to push the box out of the way. So I want you to pause and sketch that free body diagram. Okay, so I'm going to draw my box here. From the center, I've got a force of gravity with a normal force equaling that because it's not going through the workbench. I'm trying to apply a force to push it out of the way, and there will be some friction getting in the way there. Whether it's kinetic or static will depend if it's moving or not. Okay, so I'm trying to push against the box with a force of 25 newtons. Let's see if anything will happen. Okay, so I need to find my static friction. Force of friction that is static. And so I'm going to need my mu, and I'm going to need my normal force, which basically means I'm going to need my force of gravity, which is mass times the acceleration due to gravity. Okay, so my mass was 10 kilograms. My acceleration due to gravity is 9.81. And my mu, because it is steel on steel, my mu is going to be 0.74. Okay, so I substitute all those values in, and I should get a static friction of 72.594 newtons. So nothing will happen because that static friction is too big. The 25 newtons will not move it, will not be greater than it. Nothing will happen. Okay. Well, what if I instead push with a force of 73 newtons? Now, we've got a difference here of, so if I look here, my applied force is 74 newtons, and my force of friction is 73 newtons. My bad. 73 newtons and 72.9, where was it? No, oh, sorry, 659. So there will be a slight movement depending on how you've rounded. If I go back here, I could have actually argued that I should only have 2 digits and that this should have been equal to 73 newtons, in which case nothing would happen here. Okay, so this is why sometimes the decimals are very important. Okay, so let's take a look at what happens if I push with 100 newtons. Awesome, something will happen, right? Now, I'm not going to worry about the gravity and the normal. They cancel each other out. So I know that the net force is going to be my applied force minus my frictional force. Now, once I get over that, I should probably find my frictional force, my kinetic frictional force. Okay, so that's mu kinetic times my normal force, my mu kinetic 0.57, and so I multiply that by my 0.57, multiply that by my normal force from before, and I should get 55.9 newtons. So if I take my 100 newtons minus my 50, you know what, it should be probably rounded to 56 newtons because this has 2 digits. So we'll say 56 newtons, and that should get me 44 newtons. Yes, something will happen. It will move. If I want to, I could even take it a step further and say, you know what, the acceleration is equal to the force divided by the mass. So my 44 newtons divided by 10, 4.4 meters per second squared. And I can use that and I can actually calculate different things with it. Okay, so that's if everything's moving like just back and forth. That's not very real world. So let's take into account things about pushing in angles. So let's take a look at this example. So we got a person who's pushing a 49 kilogram box and he's pushing a 49 kilogram box and he is so the applied force of 950 newtons is at an angle shown in this illustration. And the coefficient of kinetic friction is 0.37, and we want to find the acceleration. Okay, so we need to find, so we know it's not going to be accelerating up or down, but we're going to need to find the force of gravity anyway, because we need to find the normal force. Now my mass is 49 and my acceleration to gravity is there. And so that's going to be, where is it here? That's going to be, oh, my apologies. I made an error. Oh my goodness. This actually question is way more complex than I thought. See, errors can happen. So let me erase this. And let's start over. All right, I'm going to start by looking at this. Okay, so if I use this free body diagram here, I've got gravity coming out of here, right? I've got a normal force, which I'll talk about a little bit here, and then I'm going to have friction. Okay, I've got an applied force going this way. I'm going to call it X because it's going the X direction. But I've also got part of that force is going down as well. Right, you can see from the angle here. So I'm going to call this one force Y. Now my normal force is going to be going up. However, that's not going to be just the force of gravity like it would be normally, right? It's also going to be keeping that downward push from pushing it through the table. So it's going to have to be equal to the force of Y. And then I'm going to have friction, which is going to be equal to my constant, my kinetic constant times my normal force. Okay. Oh, a little bit more complicated than it first looks. Well, first let's take a look at everything happening in the Y direction. Okay, so let's go Y direction. Okay, so we already know that overall I'm having no net force, right? And then I already said that my normal force is going to be equal to my force of gravity plus my Y component of that applied force. Okay, so force of gravity is easy. We almost found that earlier, 49 times 9.81. That's going to be 481 newtons. Awesome. Now, for this here, I'm going to draw this over here. We've got this bit here, and it's got a Y component and an X component and a 20-degree angle. So this is my Y, this is my X, and this here is 950. So using sine, cosine, and tangent, in this case, to find the Fy, I'm going to use cosine. So to rearrange, I'm going to go 950 times the cosine of 20. Okay. And that will get me, where is it here? 325 newtons. So my total normal force has got to be 806 newtons. Okay. Which means now let's take a look at the X direction. Okay, so my net force is going to be my applied force in the x direction. And since friction is going the opposite direction, my force of friction, which I'm just going to write as mu force there. Okay, so let's just find this here. My force in the x direction is very similar to what I found out for the y. And I hear the neighbor's dogs are going. But it's going to be sine based off of this triangle over here. And that is going to be 839 newtons. Now my force of friction is going to be mu times the force, the normal force. So that's going to be 0.37 times my 806. And so that's going to be 298 newtons. So I'm going to have 839, where is it, minus 298, and that's going to be 595 newtons. Okay, but we're trying to find acceleration, right? Well, if we take that and divide it by the mass, take that force divided by the mass, we should get our final bit here. So I'm just going to do this over here. Acceleration is equal to our 595 newtons divided by our mass of 49 kilograms. And we should get 12 meters per second squared. A big question, eh? So that's the problem with these friction questions is they often will have multiple steps. Okay, your practice is going to be the worksheet called number 9, friction practice. The answer keys should be included in there. All right, good luck, and we'll see you guys next time.